These are Riley's memories, and they're mostly happy, you'll notice, not to brag.
In this video, we'll talk about the relationship between the primal and dual simplex tableaus, and we'll discuss the idea of the dual simplex method that takes advantage of this relationship and can be used in several important contexts. So let's consider this example that shows a primal LP in canonical maximization form, and then we have the dual in the canonical minimization form, which was converted into a maximization problem by multiplying the objective by -1. In order to obtain the initial tableau for both primal and dual, we start by converting each problem in the standard form. We do this by adding the slack variables S1 and S2 for the primal problem, and then subtracting the excess variables E1, E2, and E3 for the dual problem. So then, instead of inequalities, we will have the equalities in both cases. So then we obtain the following initial tableau for the primal problem. For the dual problem, when we convert things in the tableau form, we also need to multiply all the constraints by -1 on both sides in order to make sure that you have the identity matrix corresponding to the excess variables, which are used as basic variables, right? So here we have the identity matrix for excess variables, and because of that we had to multiply everything by -1, and as a result the right hand sides become -4, 13 and -7 instead of 4, -13 and 7. Next we are going to look at the correspondence between these two tableaus. So first, note that the basic solution given by this dual tableau is not feasible because we have some of the right-hand sides negative. So we cannot use E1, E2, and E3 as the starting basic variables. And the primal tableau is feasible on the other hand. So we have positive right-hand sides here. Now let's look at the correspondence between the primal and dual tableau. First of all, let's look at row 0 of the primal tableau and see where it appears in the dual tableau. So we have -4, 13 and -7, and recall that the objective coefficients of the primal appear in the right hand side of the dual. And then when we look at the tableau, we see that this is exactly where the coefficients from row 0 of primal tableau appear in the dual tableau. So they were just copied from here to here. So then let's look at what variables are basic and observe the correspondence between these basic variables in the dual tableau and the non-basic variables in the primal tableau. So obviously only non-basic variables can have non-zero entries in row 0 of this tableau here. And these appear in the right hand side as the values for the basic variables. So we can see that the columns of the non-basic variables correspond to the rows of the basic variables in the dual tableau. And not surprisingly, the column for x1 corresponds to the row of e1. And we know this close relationship between x1 and e1. Then similarly x2, e2 and x3, e3. So these are the variables that correspond to the same dual constraints. So x1 corresponds to the first dual constraint, and so does e1, and so on. This is one thing to observe. Whenever you have a non-basic variable for the primal problem, its corresponding dual variable will be basic in the dual tableau, in the initial pair of tableaus. And recall from complementary slackness that we have the correspondence of xj's and ej's, and we have also the correspondence of si's and yi's, right? So here s1 and s2 are basic variables, and y1 and y2 are non-basic. So whatever variable is basic in the primal tableau, its corresponding variable in these pairs here in the dual tableau is going to be non-basic, and the other way around, right? So a non-basic variable in the primal tableau corresponds to a basic variable in the dual tableau. So now similarly, the right hand sides of the primal problem appear in row 0 of the dual problem. Again, not surprisingly, right? So because we are well aware of this correspondence. And then looking at the entries in the columns for the constraints, looking at, let's say, the column for x1, we would expect these coefficients to appear in the row corresponding to E1 in the dual tableau, right? And this is exactly what we observe, but we see that the sign of these coefficients is flipped compared to what we have in the primal tableau. And this is because we had to multiply all the dual constraints by -1 in order to make sure that we have the identity matrix for the excess variables here, right? And we can observe this correspondence for all other columns. So you have 2, -3 here for variable x2, then the dual variable corresponding to x2 would be e2, and we observe these same coefficients appearing as the coefficients for y1 and y2 in the row of e2 in the dual tableau. So then for the x3 column, it's the same thing, right? So we have 5, 2 here, -5, -2 here. And again, here we had the rows for S1 and S2, and they correspond to the columns for Y1 and Y2. So not surprisingly, things were essentially transposed, and then with row 0 and right-hand sides, these signs were preserved, but with the entries corresponding to the constraints, the signs were reversed. Alright, so and what remains, what we didn't mark here, are the identity matrices corresponding to the slack variables here and to the excess variables here. So, and of course, these matrices are of different sizes because the problems have a different number of basic variables. So let's keep this correspondence as we proceed with the steps of the simplex method. And the correspondence I'm talking about is the following. Whenever xj is a basic variable in the primal tableau, then ej is gonna be non-basic in the dual tableau, and vice versa. If xj is non-basic, then ej is basic. And similarly with si-yi pairs. Alright, so let's look at another pair of tableaus with this correspondence. So here we have the basic variables given by x1 and s1. So we see that this tableau is one simplex steps away from the initial tableau, but this was not a valid simplex step as we do it in order to find the optimal solution. We just picked an entering variable which is x1 and a leaving variable which was s2, and we've done the corresponding pivot. So as we see, this pivot results in an infeasible primal simplex tableau. But again, our goal here is not to solve the problem using the simplex method, but to show this correspondence between the primal and dual tableau. And you know, we can perform an infeasible simplex step just to see what basic solution corresponds to this step, and this basic solution happens to be infeasible for the primal tableau, as we see. Now for the dual tableau, this corresponds to taking e1, which is the variable corresponding to x1, as the leaving variable because it was in the basis, right? And then here we had s2 as the leaving variable, so this means that the corresponding dual variable, which is y2, will be entered. So here we had y2 as non-basic, and now y2 became basic in this tableau. So as long as we keep the correspondence between the basic and non-basic variables of the primal and dual that we were talking about, we will have the same observation hold regarding the coefficients in the tableau. The entries from row 0 of the primal tableau are going to appear in the right-hand side of the dual tableau. The entries from the right-hand side of the primal tableau are going to appear in the row 0 of the dual tableau with no sign changes. And the entries of the coefficients of the constraints in the primal tableau are going to appear with the opposite signs in the dual tableau, just like we observed before. You can see that this correspondence is shown by using the same colors for the entries in the columns of the primal and the corresponding rows of the dual. And one more thing I want to turn your attention to here is the value of the objective. All right, so the value of the objective in the primal and in the dual appear with the opposite signs, but this is because we converted the original dual problem from minimization into maximization, so we have negative W instead of W here, but otherwise the primal and dual objectives match as well. So since the objectives of the primal and dual match, we could claim optimality as soon as we have the feasibility for both primal and dual. But so far, considering these pairs here, we had the feasible tableau for the primal, but infeasible for the dual, and therefore, even though the objectives match, we could not claim optimality for either of the two. And note that whenever the feasibility condition is satisfied for the primal, the optimality condition is satisfied for the dual, and vice versa. If the feasibility condition is satisfied for the dual, then the optimality condition is satisfied for the primal. So you see, you don't have any entries with negative sign in row 0 of the primal in this case. And here you have a feasible dual tableau. But of course, because the primal solution is infeasible, we cannot claim optimality for the primal problem. And here we cannot claim optimality for the dual problem because the optimality criterion for the dual is not satisfied. So as we go through the iterations of the simplex method, if we look at the pairs of primal and dual that correspond to each other, then we will see that this correspondence that we just mentioned will be preserved throughout. So we'll have the matching objectives, we have the correspondence that we discussed in detail between the primal and dual tableaus. So, and once again, as soon as we reach the point where the corresponding primal and dual tableaus are feasible, then because the objectives match, we are going to obtain the optimal solution for the primal and the dual problem at once. So now let's look at the pair of the primal and dual tableaus that we just considered again. And first I want to note that all the entries in both tableaus can be obtained by using the revised simplex formulas that we have summarized in this revised tableau that we previously developed. All we need to know is the initial problem data, so essentially initial primal tableau, which will give us all the matrices that we need in this computation. So for example, to obtain the matrix B, we would need to take the columns corresponding to x1 and s1 from the matrix A that we have in the original tableau. Then to obtain matrix N, we would just look at the columns corresponding to the non-basic variables. And then we can use these computations here to reproduce both of these tables relatively easily. So, but now when you look at the primal and dual tableaus, we saw the clear correspondence between the two, but then, if I asked you to reproduce the dual table based on the primal, you would probably expect to be able to do it in an easier way, because let's say if I look here at -3, 11, then yes, we do know that these numbers will appear in the E2 row in the dual tableau with the opposite signs, and they do appear in that row, but then they're kind of spread apart, and it would be nice if we were able to obtain the dual tableau by just transposing the primal tableau without thinking too much. And we can actually do this if we specify all the information about the primal and dual solutions corresponding to these tableaus explicitly. Okay, so what we are going to do, we are going to add the information about the non-basic variables in these tableaus. Usually we don't have to spell out the fact that the non-basic variables are set to 0 to obtain a basic solution, right? It's easy to remember and would use extra space to spell out. But the fact that we don't spell the values of the non-basic variables out is the reason why we cannot just take the transpose of this tableau and obtain the corresponding dual tableau. So next we are going to add this information. Even though it is redundant under normal circumstances, we'll add it in order to be able to easily write the dual tableau based on the primal without thinking too hard. So here is what we're gonna call our big fat explicit simplex tableau. Alright, so here we spell everything out explicitly. So remember that we had our basic rows given by the variables x1 and s1. So these were the rows that we had there before. And here we also added extra rows corresponding to the non-basic variables. Alright, so and the way we added these rows, we made sure that we preserve the sequence in which we wrote the variables in the column. So it's x1, x2, x3, s1, s2. And then we mixed up the basic and non-basic variables here by writing them in the same exact order as we wrote the columns. So here we could have written the coefficient of 1 instead of -1. Either way, it would express the same fact that x2 is equal to 0, and the same with other non-basic variables. But we use -1 here because the entry in corresponding row and column of the dual tableau will be equal to 1, because the variable e2 corresponding to x2 in the dual tableau will be basic, so it will have the entry of 1 in that position. And remember that for the coefficients of the constraints, we reverse the sign when we switch from the primal to the dual, so we'll use -1 here just to keep that intact. Alright, so similarly for the dual tableau, we are also adding the rows corresponding to the non-basic variables. Here we had the basic variables e2, e3 before, and then y2 was the third basic variable. And we added 2 extra rows corresponding to the non-basic variables, and the rule was the same. We used the coefficient of -1 and the rest of the entries in that row is equal to 0. So this expresses the fact that e1 is equal to 0, and similarly for y1 we have the constraint -y1 is equal to 0, which is the same as saying that y1 is equal to 0. Alright, so once we added these rows, we also add for convenience here the correspondence between primal and dual variables. So we added this row on top of the primal tableau just to show that x1 corresponds to e1, x2 to e2, and so on. And we did the same thing with the dual tableau. And note that for the dual objective that corresponds to the right hand side of the primal, we write here plus minus w, because for the objective value we have here plus w, but if you look at this column of right hand sides here, then it corresponds to the coefficients in the objective for -w. Similarly, we add the row describing the correspondence to the dual variables of the primal variables on top of the dual simplex tableau, and here we also have negative plus z, because the right hand sides correspond to the coefficients in the objective for z, which is plus z, and then the objective value corresponds to negative z, so that's why we have negative on top here. Alright, so other than that, also it is important to note that the order in which we specify the dual variables in the dual tableau, both in columns and rows, corresponds to the order of the corresponding primal variables. Instead of writing y1, y2, and then e1, e2, e3, first we specify e1, e2, e3, which correspond to the primal variables x1, x2, x3, just to keep the same order as we have here, and make sure that this correspondence between primal and dual is 1-to-1, and all we need to do now with the primal expanded tableau is just transpose it in order to obtain the corresponding dual tableau. So now it is apparent that if I just look at this matrix of the coefficients for the constraints, then the transpose of this matrix is gonna be given here, with signs reversed, of course. So let's say if I look at the first column of this matrix, it is appearing as the first row of this matrix with the negative signs, and then the second column appears as the second row here with the signs reversed, and so on. So you can see this correspondence for every column of the primal and row of the dual, and then we just copy row 0 from the primal to the right hand side of the dual. We copy the right hand side of the primal to row 0 of the dual, and then we reverse the sign of the objective value and put it right here. So in this way we obtain the explicit dual tableau. But of course, normally we don't really need these rows for the non-basic variables, and we can just cross them out once we completed this conversion. Alright, so this way we can easily obtain the dual tableau from the primal tableau. And now recall that previously we mentioned that having the optimality condition satisfied for the primal problem in row 0 corresponds to having the right hand sides being all non-negative in the corresponding dual tableau. And in order to find the optimal solution, what we need to do, we just need to ensure feasibility of both primal and dual. So and then this ensures also the optimality of both primal and dual by this correspondence. Right? So, but in some situations we may have the tableau for the primal in which the basic solution isn't feasible, just like what we observe here. So there is a negative 4 among the right hand sides, meaning that this basic solution isn't feasible. But we see that at the same time in row 0 we have all non-negative coefficients, which means that if we switch to the dual, then we'll have a dual feasible tableau. Alright, so and remember that with the simplex method, getting a starting feasible solution is non-trivial, so we would have to apply methods like two-phase or big M in order to find the starting solution. But if row 0 is non-negative, then it is easier to just switch to the dual and apply the simplex steps for the dual. So this is what we call the dual simplex method.
I don't want to get too technical, but
the dual simplex method is essentially applying the simplex iteration for the dual tableau, but writing them in terms of the data for the primal tableau. By applying the simplex steps on the dual tableau, what will happen with the primal tableau at the same time? If you write down the corresponding primal tableau for every iteration, then what you will have will be optimality condition satisfied for the primal at every iteration, but feasibility condition not satisfied until you reach the optimal solution, right? So, but essentially the iterations of the dual simplex method are equivalent to taking the primal tableau, then transforming it to the corresponding dual tableau and applying the usual simplex steps to the dual tableau. So this is what the idea of the dual simplex method is. Now, why is it important? Because very often when we have the change to the original problem data, what will happen, just like we saw with the graphical sensitivity analysis, applying certain transformation to the constraint right hand sides may make the previously optimal solution infeasible. So then what do? In this situation, it may make sense to switch to the dual problem, because usually, let's say, if I change the right hand side of the constraint, the optimality condition will not be violated, only the feasibility condition will be violated. But this means that if I switch to the dual, I will have a feasible but not optimal tableau, right? So then by applying the simplex steps to the dual problem, we can solve both dual and primal. Note that in our explicit tableaus here, it's very easy to see how the complementary slackness condition is satisfied, as whenever one of the two variables in the primal dual pair is basic, the other one is non-basic, therefore their product will always be equal to 0 in every step of the simplex method. And also the objectives match at every step, Therefore, the only thing that is lacking in order to have the optimality of both primal and dual is the feasibility for both primal and dual. So once you get feasibility for both primal and dual, you are guaranteed to have optimality for both of them. And finally, I would like to add that when we talked about the duality theorem, the way we showed that the duality theorem holds using an example, we just read essentially the optimal dual solution from row 0 of the optimal simplex tableau for the primal. Right? And we can see now that this was not a coincidence. In fact, every time we run the steps of the primal simplex, we are simultaneously solving the dual problem as well. It's just the values of the variables for the dual problem are read in row 0 of the primal simplex tableau. And then when we apply the primal simplex tableau, all of these values are kept non-negative. Remember, we use the ratio test to ensure that we have feasibility at every step. And then when we find the optimal solution, all of these values also become non-negative. And as a result, we will also obtain the optimal solution for the dual that we can easily read from the optimal tableau of the primal. So now this should be explicitly clear. To conclude, I would like to reiterate that if the primal simplex tableau is infeasible but all entries in its Z-row are non-negative, so this means essentially that the optimality criterion is satisfied and the only thing that's missing is feasibility, then the corresponding dual tableau is feasible, right? So because having non-negative entries in row 0 ensure that you'll have the positive or non-negative right-hand sides in the dual tableau. Therefore, in cases like this, it makes sense to switch to the dual tableau in order to solve the problem using the simplex method. And then when we apply the primal simplex steps on the dual tableau, this is essentially equivalent to using the dual simplex method. So this approach is particularly useful when we change the problem data, and as a result of this change, the solution that used to be optimal for the primal LP now becomes infeasible, and in order to find the new optimal solution, it's easier to switch to the dual, and intuitively you will not need to put too much effort into finding the new optimal solution if the change to the problem was not very dramatic. Alright, so and this will be the next topic of our discussion, so you'll see how exactly all of this is applied in the context of sensitivity analysis.
This actually feels kind of nice.
Okay, here we go. We'll be back to headquarters before morning. We can do it. This'll be easy. This is working.